good taste and stability of oxidizing. So we studied the chemistry of these. Okay, here is a combination of phytochemistry and nanochemistry. So we figured out that quercetin and lutein are the main component of leaf extract or extract of this plant. So we tried to synthesize gold nanoparticles with the help of this simple extract, which is 100% biocompatible. Everything is in water. No chemical is used. So we play too many parameters: temperature, ratio of starting materials, volume of solvent, time of stirring, and too many things. Then you can get different size of nanoparticle. And this thick layer is organic components of extract, which is also as a stabilizing agent. So, with this in mind, I got a good opportunity to join Professor Mustafa's group. So, we started with this kind of people in the lab here. Actually, they have started, I joined to this research. Very similar research area we were following, me and Professor Sina. So, this is Sohila. Actually, she has used kassoon leaf extract, which has gallic acid, quercetin, mycetin, flavonoids. Flavonoids are very well-known antioxidant compounds. So simply, you add a leaf extract to aqueous solution of gold, and you get this colorful gold stable nanoparticle. And this is the optical absorption of gold ion leaf extract, and then adding them together, you see surface plasmon bond showing gold nanoparticle formation. And of course, you need to look at the size, look at the geometry, look at the shape, and these are almost icosahedral, and some are also triangle nanoparticles form. Also, here we are interested and working on this idea. How about putting silica layer and magnetite and functionalize this coastal system with a good ligands, let's say SH, NH2, and of course metformin, to absorb metal ions, and then use this leaf extract as reducing agent to have these nanoparticles form at interface of solution and this coastal system, and use them again in organic chemistry, simple organic chemistry reaction as catalyst. So, also one interesting finding, we came up with this result. Very quick explanation. Bunga content, am I right? Leaf extract you can use to prepare gold nanoparticles and of course palladium nanoparticles separate. But the interesting thing is here, based on this UV absorption, we are able to target different shape of gold nanoparticle. As it is proved with the help of TM. You see everything, hexagonal, triangle, spherical, everything, even bar, nanobar, nanoprism, everything of gold. With the help of this, again, reducing agents found in leaf extract. But when you add these two to together, okay, when you add them together, you only see spherical, almost spherical particles, which are nanoalloy made from gold and palladium. We believe, we are still working on that to prove this claim. We believe, just because of low and easy reduction potential of palladium, you have palladium ions, gold ions, and leaf extract. Leaf extract is reducing agent, and of course stabilizing agent. Once you add it to the solution, bimetallic ion solution, first, palladium ions are getting reduced palladium zero because of the easy reduction potential. Then, gold ions after 20 minutes, 15 minutes, then you will see gold ions are also getting reduced and forming nanoparticles. But palladium nanoparticles already formed are like seeds. So gold nanoparticles are forming at the surface. Or maybe there's another idea. We have to think and we have to go on, work on them. But if you look at here, if you look at this image, this is, I would say, nanoalloy, but these are palladium, just palladium nanoparticles. Because once you have few nanoparticles made from palladium, okay, gold, equivalent of gold is too much. So you will get gold instead of palladium at the surface. You have extra monometal palladium nanoparticle form and bimetallic form here. And of course, almost controlled size and shape. No triangle, no hexagonal, and other form that we saw in the previous case. So we believe this is a seed control synthesis of gold nanoparticles with the help of in situ generation of palladium nanoparticles, with the help of leaf extract. So, yeah, please here again, you can simply see the EDX result here, too many palladium here, and compare with the percentage here. This is almost half of them, but look at here. This is most made from gold and some palladium, but here you have, let's say, 2 of gold and 1 of palladium. Okay, I think 45 minutes is over and done. But I would like to say these works always are being done with the help of students. Without the students, we can't do this research. We can't follow our design in chemistry, nanochemistry. So I would like to thank to few of my group members. This is just the backside of my office in Universiti. We have 2 high mountains in backyard. Sometimes we go and we have some breakfast. I have been working with too many people, but I'm very lucky that I have very, very, very good and kind students. Very good group, active and in point of departmentship, very helpful. So I like this atmosphere. Of course, yesterday, no, the day before, was my birthday. So I saw the same atmosphere here at UTM. This is my birthday cake. Thanks to all of you. Of course, Atika is not here, and Fredo is not here. We kept your cake. I'm not sure if you had it or not. No. So, of course, last but not least, I would like to again thank you, all of you, and appreciate your time being here and listening to my research interest and work. If you have any question, I'll be happy to answer.
Okay, thank you very much for a nice presentation. Any question from the floor? Comments?
Very nice presentation. Excellent. My question is, how do you separate this palladium or gold nanoparticles from the leaf extract?
Which country?
Malaysia.
Which country? Because
Malaysia,
I asked you,
yeah.
if you have a question, please just give me the place.
Malaysia, UTM.
Okay. How can
you separate this as a powder or something? This is my idea. This palladium gold nanoparticles.
bimetallic? Are you asking
Yeah,
about bimetallic?
You have this gold complex and
we
you put the leaf
You
extract.
are asking about those that TEM we have.
Yeah, it's
Extra-
the leaf extract.
It's very difficult to separate them. So that's why now we are trying to vary in too many parameters to get rid of those extra mono here. Please. Yeah, to get rid of these extra, I would say almost mono palladium nanoparticles. It's very difficult to separate them.
You should use some strong acids.
To wash them.
Yeah.
Maybe we alter the surface
Texture.
for bimetallic.
Texture.
Yeah. Actually, we are not going to use any chemical. Just water and nature. Yes, easily. Yeah. With the help of centrifuge.
Thank you.
Okay, is there any question? Okay, let's go to the Canada.
Yeah, sure. Why not? 6 months now.
So you are talking about the sensor of gold nanoparticles when it can be used as a good sensor for lead.
Yeah.
And you mentioned that the naked colorimetric sensor was based on the difference of the agglomeration happen when you have lead.
Before and after adding it.
Yeah. So when you add lead, I could not understand why the silver can be agglomerated, and after you detect this lead, can be reused back. I mean, if you take out the lead, will the agglomerated gold nanoparticles return to the initial size?
You mean can we reuse it?
Yes.
Because we have to remove palladium lead.
Lead.
If you wash it with another strong ligand, which is KF, complex formation constant, is more larger than KF of chrome ether and lead, then like in the case of, I know in the case of, for example, calcium, you can use EDTA. You can wash any complex with a solution of EDTA, you get back the calcium. But we actually we didn't try this. We published this paper in Teknologi from IIP, which I really like that paper. So actually it was for 1 week as what do you call it? They call it nanotalk up there in their site. So too many comments I got from too many interested people, and most of them were asking about commercialization. How can we make cheap? Let's say not cheap, CHEAP, and paper-based kit, test kit. So if you use filter paper, and you soak it in gold nanoparticle solution modified with azachromiter, you will have a thin layer at the surface. Then, if you take it and soak it in lead-containing solution, you will easily see the color change. But the problem is, if you want to remove lead, maybe you will remove also the whole non-particles on the surface. But if you do that, of course, it will be very, very useful.
Okay, thank you very much. Anyone wants to go to Ireland? We have been to Canada and Malaysia. Another one country? No one? Okay, let's go to Iran. So we have the whole three countries. Is it able to go to
Iran.
So you do the
studentship time or my
I
job?
don't remember. Just, I think the mechanism for the reaction when you use silica using the palladium complex. Yeah. You mentioned on in the mechanism it's mentioned that you use palladium 2+ in the first, and then it was after reaction it was reduced to palladium 0. Okay.
Because it was clear from T.
Yeah. So my question will be, we know that palladium 0 is also the active species, so no need to have that palladium 2+ instead of palladium 0. Yeah. So do you check the activity of palladium 0? That's the first question. And the second question, when you have the oxidation here, it becomes palladium 2+, so becomes palladium 0 and have the cycle. When it was reduced and when it was oxidated, what happened with the ligands?
You know, when it is in palladium 0,4, I'm asking you the second question first. When it is palladium 0, it is stuck within the pores. There's no complexation, right?
Yeah. So where are the ligands there?
Stay there.
Still there.
But there is no complex complex formation anymore between palladium 0 and metformin. Just physically trapped nanoparticles. But for you answering your first question, it doesn't matter. Either you have palladium 0 or this. This is if you have complex varying palladium 2 or palladium 0 at the surface, because this is the cycle. You start with this, you get your product, you have these palladium 0 nanoparticles physically stacked, embedded within the pores, but with the help of oxygen, it doesn't matter. They can again. This is the ligand attached to the surface after palladium 0 nanoparticle formation. It's free, but with the help of air, you have these two together. Again, you have your starting catalyst.
So when we are asked what the active site, is it 2+ or 0?
Still have no answer.
If
to be honest.
So, okay.
Yeah.
Because if we check the activity of palladium 0 may be.
Palladium 0, the problem with palladium 0 is leaching. You know, if you run 4 times with the help of palladium 0, physically absorbable, you will actually not be able to use it for several times. But when you have it as complex here, you can use it for 15, 14 times. Because it's chemically, covalently, coordinated, not covalently, it's coordinated to the surface. But here, this is just embedded, physically embedded. If you wash it, if you alter it, maybe it will leach out immediately into the solution.
Okay, thank you very much. So we have already 3 countries mentioned and explained. So if you have any other question, you can ask directly to Associate Professor Dr. Alizadeh. And after this, you will have plenty time to discuss if you want to have the discussion. So I would like to invite our director, Prof. Mustafa, to give the certificate to our speaker today. With this, we end our session, our seminar series. I hope we can see you again next